Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
What we've done in the past is we've talked about some things that got fairly esoteric and detailed, and we wanted to be able to apply them later. But we were trying out some new tools. Today we're not going to be trying out new tools because we pretty well have them down. So we're going to try to ease into a buck and a boost converter. And we demoed those a little bit last time. We have PCB design of each of those, and we want to be able to look to that. So we'll be doing that later on in the session. First, let's just start talking about what we're doing here. Okay, I have up my first slide is a duty cycle into an RC filter. Let's ease into a buck in such a way that it makes a lot of intuitive sense. And we'll talk about the technical topics too as we go past them, but let's just try to take it on a simple basis. Okay, first, let's start off with a duty cycle control. You all are familiar with the duty cycle control. That's where the on time is a certain fraction of the total time in a period, and you basically have an on-off type pulse width modulation kind of signal. So if it's on 25% of the time, well then it would be called a 25% duty cycle. If you take that duty cycle and feed it into a thresholder, a limiter, something that goes between two specific voltages, in the particular case we're talking about, we're looking at 0 and 1, then the voltages coming out of that will be switching between 0 and 1 volt. If I take that voltage and then run it into a simple RC filter, I will find that what I get out is the DC. If the RC filter were perfect and threw all of the ripple away, I would get out a DC voltage. And that DC voltage would be equal to the 1 volt times the duty cycle, whatever that is. Now there's obviously a lag. If I change the duty cycle, it'll take a little while for the RC filter to catch up and adapt. But it turns out the RC filter isn't perfect. It has a roll-off frequency. The frequency is 1 over RC in the radians domain. If you take it in the frequency domain, it's 1 over 2 pi RC. And that's the kind of the frequency at which it starts. That's the frequency of the cutoff of that RC. Now, that will be rolling off, since it's a single pole filter, at 20 dB per decade. And so if we switch at some higher frequency than that, we will be throwing away a certain amount of that 0 to 1 volt switching energy and ending up with a smaller, more triangular shaped ripple. So if you look down at the bottom of the curve, what you'll see is you'll see a dB plot versus log frequency. You'll see an F0 frequency in there, below which the ripple is going to be constant. That's basically 0 to 1 volt, and the RC frequency is too high to help. And as you go up in frequency past F0, it starts rolling off at 20 dB per decade. Somewhere up above there, we come to a switching frequency denoted by FSW. And F switch is going to be the switching frequency that we're going to be using of the duty cycle control. And if you then find out where the intercept of that is, you can find out the ripple voltage. So that's kind of in a graphical way what we're trying to do. So let's look at this a little further. What happens if, well, let's go back to this for 1 second. What happens to this RC filter if I put a load on it? What if I put another resistor on it, a series resistance on the output? So let's assume that I take that and I put another resistor to ground on the output. All right, now I have a load resistor. Well, the net resistance that is seen by this filter is R in parallel with RL. Therefore, it's going to shift the frequency. Not only that, the R and the RL form a series voltage divider. So my output voltage is going to be lower than it would be otherwise. So that could be a problem. If we go to an LC filter instead, there's some magic things that happen. First, there's not much resistance in series with the LC, so if we do add the resistor on the end, it doesn't affect the DC value. It stays about the same. So we have a lot less to deal with. Second, we don't have the loss of the series resistor because the inductor is, for the most part, lossless. Of course, there is some series resistance we could deal with. But notice also that the resistor has, the LC filter has a roll-off of 40 dB because it's a two-pole filter. Now what happens down below is instead of having the red line, which is only 20 dB per decade, we have a roll-off twice that, which is 40 dB per decade. That means that the switching frequency can be much closer to the cutoff frequency of the LC filter. That's really important when you don't have to have so many decades of frequency change. Inductors and capacitors have certain high-frequency limits, and you need to stay pretty far away from them to be able to keep efficiencies up. So that really, really helps. So hence, we have something here that is taking a VCC and ground, some source voltage. In this case, we're assuming it's 1 volt, but it could be whatever. We're running it through a duty cycle, and we're coming out with a different voltage on the load. And that voltage on the load is controlled by the duty cycle. What we have here, in essence, is a buck converter. Now, we can do the same thing instead, but use BJTs as drivers, but there are some problems with BJTs. First of all, BJTs always have a certain amount of loss in them. They cannot turn on completely. So there's like about 0.3 volts VCE sat in every case, and that 0.3 volts is going to prevent you from pulling all the way up to the rails. So it's not going to be exactly perfect. We have about 0.3 volts VCE sat when they turn on. Another problem is that the junction voltage is probably about 0.75 volts, 3/4 of a volt, from the base to the emitter in each case. Now, it turns out if we have some beta, say we have a beta of 20 in this case, it could even be less than that, then whatever current is being drawn down through the device, let's say we have some current flowing down through the device, we're going to have about 1/20th of that. So if we had 10 amps flowing down through the device, we would have 1/20th of that, or about 1/2 amp flowing in the base. Well, that turns out to be a significant amount of loss. 1/2 amp times 0.75 volts is going to be 375 milliwatts. And so that's going to add up. Okay, but there's even one more significant problem. If we have inductor current flowing out through the inductor, it's going to keep flowing. We'll typically be switching much faster than the time would take the inductor to completely run out and stop. So if we suddenly alternate, we have our time number 1 where we're switching in number 1. And the current is ramping up. But at time number 2, the current is ramping down. Where's that current coming from? The upper switch turns off. Instead, the current needs to come up through the bottom switch. But it turns out BJTs have very terrible betas if the current is going the wrong direction. They do not work well. So it's going to be absolutely imperative that we have to add another diode. And that diode is key to keeping that current flowing unless you go to a discontinuous mode. That diode, again, will have, say, 0.75 volts of drop, but it now has the full current. It has the 10 amps flowing through it. So that's a much higher power loss. That's 7.5 watts being dropped in that diode. So this can be a fairly inefficient kind of a circuit to use for BJTs. All right, so what can we do about this? Well, to decrease the heat, we can consider going to another kind of a device that you're commonly familiar with. We have MOSFETs as drivers. Now, MOSFETs are wonderful devices because they typically have very, very low on resistances. and very, very low drive requirements. A typical MOSFET can be down at 10 amps. They can go up to over 100 amps now, and they have on resistances in the range of 1 to 10 milliohms on. So the amount of drop that you would get at 10 amps and say 3 milliohms would be in the neighborhood of about 30 millivolts. And again, if you do the math again, you'll find out that's approximately 300 milliwatts. So the total watts is pretty low. And that's 300 milliwatts if it was continuous. It's actually 50% in this one and 50% in the other one, because only one is on at any given point in time. Note that on the gates, the voltage on a gate typically, if you read many specs, can go both positive and negative with respect to the source. So it can be like plus or minus 20 volts, a large voltage. And when you need to go up to, say, 5 volts above the source to be able to turn on. But you can reverse bias it a lot. It usually is fine. And you can also take it far up over the voltage where you can't do that with a BJT. In a BJT, the base emitter junction turns on and starts conducting a lot of current. So this is, and also once you get the gate charged up, there's essentially no current flowing in it at all. Okay, so we have some oscillator driver. It can be one oscillator driver that basically is going from the low voltage all the way up to the high voltage if you want. You don't necessarily need to have some kind of floating high side driver in here, because if you get the voltage high enough, it will turn off a P-channel MOSFET at the top, and you can have an N-channel MOSFET on the bottom. If you want to use 4 N-channel MOSFETs, well, then you probably are going to want to have some kind of high side floating driver in there. But we're going to ignore that for right now and just draw it as a complementary pair of MOSFETs. In this case, we have, again, we're switching between VCC and ground. We're doing it in a MOSFET, and the current is flowing. It already has a check diode in it, so I don't need to add an external one. And when it's on, the resistance is very low. I've seen recently seen quite a few MOSFETs showing up at relatively low cost that can handle hundreds of amps and have on resistances much less than a milliohm. So this is what you'll see primarily in almost all of the drivers that are coming up because of their advantages over BJTs. Okay, so let's compare and contrast the various devices. First, we have a silicon diode. At low currents, the drop is probably about 0.7 of a volt. At fairly high currents, it could be up over a volt. And if you look at diodes near their limit, that's more likely what you will see. That's really pretty high. So how does that compare to a Schottky diode? Well, Schottky diode is more at low currents. It's more can be down in about the 350 millivolt range, and at higher currents, it can be up in the neighborhood of about a half a volt and still be supplying significant currents. So that's quite a bit less power loss in your circuit if you use Schottky diodes over silicon diodes. And Schottky diodes are also quite a bit faster. They're faster in turnoff, which helps in switching circuits. Then we get down to the MOSFET. Again, it has a regular diode in here, which if it was conducting would be the 0.7 to 1.1 volts. But again, we don't necessarily always need to use that. If we're using it in the forward condition, it's going to end up having somewhere in the neighborhood of again, 0 to 10 milliohms. So, and that is either forward or reverse. This channel is a bidirectional current channel, and so you can have current flowing either direction. Now, this is a really important concept. This is something maybe you guys haven't heard of. So, okay, let me show you this ideal power rectifier. We have a MOSFET here. Now, what happens when the voltage goes high? by the way, I'm going to put some quick values on this. If I have resistors down in the bottom that have some value R, and I have resistors up in the top that are KR, it's just a balanced differential pair that puts the signals commonly referenced around the input to the gate so that you can reduce the size of the signal and still do a differential compare. Okay, so if up at the top it's positive and down at the bottom it's negative, that's going to make the negative input more positive than the negative input. Therefore, the output is going to go low and the device is going to turn off. And this is going to have an impedance is greater than megohms. Very high, very off. Now, if I turn around on the other side and say, okay, well, what happens if the opposite direction? Well, then what you're going to see is that the same thing is reflected on the input to the op-amp. The op-amp is going to turn on. It's going to turn on the gate, and this thing is going to become a very low resistance. It's going to go down to about like 3 milliohms. But you say it's, yeah, but it's reverse biased. Yes, well, who cares? It conducts in both directions. It's a channel. Now, I'm not going to say that every last MOSFET is this way, so you should check if you're going to particularly try to do this. But you now have an active rectifier that can have an extremely high on resistance and an extremely low on resistance and extremely high off resistance, and can switch between them. And you say, well, what if this comparator takes some time to switch? You still have a diode automatically in there that's turning on anyway. It's just shortly after that diode turns on, the other channel through the comparator is going to come along and turn on the gate. So you end up with something that's going to be ideally rectifying and generating almost no power. By the way, if you guys have some questions, be sure to enter them in the chat box on the screen, and we'll get to them shortly. Again, ideal rectifier. Where are these especially useful? Well, low voltage circuits. Where are there low voltage circuits? Well, I'm sure some of you have seen, like 1.2 volt regulators and other things. Another very key place that it's coming up is in solar, where the typical voltage on a solar cell may be, 0.55 volts at the maximum power point, and possibly 8 amps in full sun. So you end up with needs for very high currents and not much drop in the reverse direction. So, okay. All right, another concept that we need to talk about that is very, very important. First, when these MOSFETs are switching on and off, sometimes the node will be pulled high, and other times the node will be pulled low. If it's a good converter, it will be doing that very, very quickly. What that means is that the rate of change of voltage, dV, the amount of voltage change, delta V, is very large. In a 12-volt circuit, it would be like a 12-volt change. Also, the amount of time it's changing in is very small. It's a microsecond or less. Okay, so we have a large voltage change and a very, very short period of time. Well, if there's stray capacitance, what's the current involved in those stray capacitance? I equals C dV dt. Well, dV dt is huge. So C dV dt is going to be pretty huge too, so the current is huge. That means that these stray capacitances can couple that switching energy, those sharp spikes, into anything in their vicinity. So it's very, very important to stop that from happening. One of the ways to do that is keep that switching node far away from anything else. The second thing you can do, which is not as good, is to try to shield it or keep things close to it so that if it does switch, that most of the capacitance is to something else, so that most of the current is going to be satisfied. There's going to be current surges, and it's going to slow down the edges, but there's going to be less dV dt, and therefore it's not going to be coupling to other things. But primarily, the goal is to keep that switching node away from anything else so that it does not capacitively induce voltage spikes on other circuits. I have a question here. Is body diode recovery time a problem? It is in some circuits. You may actually find some circuit switching, and something else is trying to pull on. I mean, a classic example is a push-pull type driver on a transformer. And one device tries to pull, the off device turns on and tries to pull one end of the coil down. That makes the other end of the coil want to go up. And it may turn out that if that transistor or device doesn't let go, you end up with a short circuit for a short period of time, causing a huge current spike. And so push-pull type outputs on transformers will suffer from reverse recovery. It's very important, if you're going to do that, to try to make sure that diodes turn off as quickly as possible. If you can't make sure, and you can't look at your timing, then you may have to put a dwell time in. But you don't normally want to do that because that makes it makes the circuit much more complex. I also have another question as to whether all MOSFETs have a body diode. All common power MOSFETs that I see today do have power diodes. Some of the very older ones didn't make them with very good diodes, and some of the other type of FETs don't necessarily have an intrinsic body diode. But all the classic power MOSFETs that you find out today that you'll look at, I think without hardly an exception, you'll find out that they do have body diodes. The characteristics of that body diode change somewhat, from transistor to transistor. So you'll really want to make sure you take a look at that if you're going to be relying on it. You wouldn't want to be, say, switching 50 amps and have a diode that can't take a spike at 50 amps. So, okay, continuing on. Another common thing that needs to be understood. These devices are switching, and there is current flowing in the inductor. Now, ideally, you'll turn one off and turn the other on at exactly the same time. And when you do that, the current will change from going through one device to going through the other device. Now, it doesn't just invent itself in the middle of thin air. It has to come from somewhere. So if it's drawing it up from ground, that's great. But suddenly, when you start drawing it down from VCC, where does that come from? Well, it actually is pulling it out of a capacitor that is tied between VCC and ground somewhere. And hopefully that capacitor is fairly close to the MOSFETs, so that current doesn't have to go a long distance down bus bar paths to actually get there. So some of the time it's going to be going down one path, and some of the time it's going to be going down another path. If we have part of the time it's going down one path, and part of the other time it's going down some other path, then you're going to see that the current is going to be switching. It's going to be constantly flowing. The current through the inductor is constant, all right, or it's changing very slowly, but it's coming from different sources. So what you really want to do is look at where that current is coming from and where it's going to, and make those paths overlap so that if it switches off of one path, it switches onto the other, but in the same place. What happens is if they're separated, each one is going to suddenly have current flowing and suddenly have current not flowing, and that current is going to create a B field, or a magnetic field around that trace, which is going to couple to other traces in its vicinity, and it's going to induce currents in those other traces. Again, the delta I at the switching time is very high because the current is turning on and off, and it's relatively large, and the delta T is very, very small, so the IDT is very, very large. So V is equal to L d I dt. So you basically are able to induce a significant voltage on anything that acts like an inductance. And remember, just a wire is an inductor. It's just kind of unkinked. So what ends up happening is if you can run them in the same place, the current, in essence, stays in the same place. It only shifts a small amount. And so the coupling to other devices cancels out. So these intermittent current loops are something that definitely need to be looked at very carefully in the design, and we'll do that when we come to a PCB. So again, here's a buck converter. Same duty cycle converter, same as the thing we've been looking at. It only has two major or simpler differences. Obviously, it has the LC filter on it, and number two, it has the lower switch is just a diode because that's all it really needs. We could put an active rectifier in there, but it's not necessary. Also circled in there in red, you will see the switching node. That's between the two switching points. That's the one that has a high amount of voltage. I could also equally draw the current path, because part of the time the current is going to be flowing through the MOSFET. The other part of the time the current is going to be flowing up through the diode. It's always going to be flowing through the inductor and capacitors. We don't worry about that. That's DC current. We're talking about the AC path. So where does this current come from? Well, assuming the power supply is fairly far away and there's inductance and things in the line, it's going to be primarily drawn through a bypass capacitor. You try to keep that bypass capacitor and or input filtering close to this device. Otherwise, all that switching noise is routing back through the entire board back to the power supply. That's where it has to come from. And hence, it's going to be coupling into all sorts of other things. When it's not, it's just going to be basically coming up from ground. So you end up looking at a loop where the current is flowing. Now, if I can keep those two loops on top of each other, if I can keep the top loop and the bottom loop on top of each other, then that would be an ideal way to reduce that type of coupling. Okay, here's a little tip. A couple of things we need to talk about. Feedback loop gain. Let's look at this circuit. This is only part of an IC. You'll see that there's an upper gate and a lower gate signal coming out of the chip driving two MOSFETs, Q1 and Q2. In between the two, you see the switching node, which is actually going back into the chip, probably for monitoring purposes. And there's also a little capacitor down the boot, which has some other function we won't go into. This particular one is supposed to run off 12 volts, which you'll see up at the top, and the negative side is at P ground, which is ground, 0 volts. The output is an LC filter, classic buck configuration, and the inductor is 2.2 microhenries, and the capacitor is 330 microfarads. It's trying to put out 3.3 volts at 10 amps. Probably the frequency switching here is about 300 kilohertz from what I can find from the literature on this particular chip. Notice also that in order to try to keep the output voltage stable, they've sampled the output voltage and sent it back to output 2 as a feedback signal. Well, this is interesting. Notice that, feedback can be really wonderful in trying to control an output voltage. If the load is going to be changing or other such things, it can handle small little shifts. Starting with an LC filter instead of an RC filter means you don't have a lot of power loss, and you also get much better direct regulation just from the duty cycle that you have, but it still may be far away, it still may drop, and you still may want to adjust it because there is some series resistance in the devices, such as in the inductor. So a very low DCR path is very useful, especially in the MOSFETs and in the ground. So we'll look at that in just a minute. But you need to be aware of feedback from circuits that are using LC filters. Well, why is that? In a nutshell, an LC filter is 2 poles, and it introduces 180 degrees phase shift when you're significantly above its resonant frequency. So you can't put that in a feedback loop that has a gain higher than unity and expect it to be stable. So you need to start rolling off with, say, a 90-degree phase shift and such that by the time you get to up to the frequency where you have the LC starting to take effect, that you're down below unity gain. Okay? In this particular case, I'm going to be calculating the cutoff frequency here. Basically 1/2 pi squared root of LC. We know what the L is and the C is. If we put that in, we come out and find out that it's about 4 kilohertz. 4 kilohertz. So if you put that in on a plot, as you see down below, and say, I need the gain around the loop to be less than unity, i.e. 0 dB, at 4.1 kilohertz, and back up from there at 20 dB per decade, you need to make sure that the low-frequency pole, the RC pole in your feedback loop, is low enough that it will, such that the loop gain will be less than unity at the cutoff frequency. So, hypothetically, just throwing 120 dB op amp in there, and not taking other things into account, it's coming up somewhere down in the 1 to 10 hertz range. You need to understand that that low frequency pole is important. It's a big topic, but LC filters require special feedback techniques. If you're not accustomed to them, you need to be a little careful. You may find a pre-compensated op-amp that has the pole somewhere down below a hertz that will work fine, but you do need to be careful of that. That's the point I'm making. So what about ripple? Assuming this is the case, let's say we have a switching frequency of 300 kilohertz. Well, that frequency is 1.568 decades above the cutoff frequency. So since it's an LC, we have minus 40 dB per decade, and so with that many decades, it comes out to 74.3 dB, which means the attenuation is going to be approximately 0.001, or about 1/1000th is going to make it through. That's pretty good attenuation. If I have 12 volts in, that means I'm going to get about 2.3 millivolts of peak-to-peak ripple out. Again, now these are rough estimates. Somebody may take me to task for a factor of 2 or something in here. But just to try to give you an idea, start off majoring in the majors. See if that's going to be acceptable. If you can't tolerate 2.3 millivolts peak-to-peak of ripple, then you need to do something different. Okay? You may need to go through an entire additional stage and make a higher voltage coming in, filter it again, and then throw it through a linear regulator or something to accomplish your needs. But for the most part, a lot of things can run off of switching power, and switching power has inherently in it some noise. So that's what we're trying to talk to today. Well, what about this feedback loop damping? They use a damping factor, the Greek letter zeta for a damping factor, and it's different for series circuits and parallel circuits. I kind of show that over the right. I don't know that it's overly interesting. I'm not going to dwell on this because we want to get to some of the circuits. But to optimally damp something, you want the damping factor to be about 1. Using the values of resistance shown for the components in the circuit, we will see that we come up with a series resistance of 34.6 ohms. Well, in order to get this to optimally damp, we're going to need a different resistance than that. If I look at it from a parallel standpoint, I get 28.9 milliohms. I thought I had calculated the damping factor in here, but I'm not seeing it, so hold on just 1 second. Yeah. Okay. I didn't calculate it. I'm not going to dwell on it, but you can actually calculate your damping factor for series RLC using the parallel values. If you compare the values that you would need to have to damp it over on the right with the values in there, it's very clear that they do not come up to the values necessary. So this circuit is not going to be damped. Therefore, warning down at the bottom, beware startup overshoot transients, which can damage circuitry. You turn on a circuit and it's supposed to regulate at 3.3 volts. Well, what if it goes up to 6 in the first second because it surges past 3.3 and then comes back? That type of thing can occur and does occur regularly. So you need to worry about it. It may not damage if it's running into a heater or something, it wouldn't matter. But if it's running into an IC, that could be terrible. You may need to have clamps on it, or better yet, use some better things. For example, soft start by controlling MOSFET gates to where you turn it on slowly. Or you can add a resistance during startup and then short it out afterwards. Series resistance basically blocks some of it. And then switch it out after things come up and get close to charge. Okay, this will be in the slides. Don't want to belabor it, but you can see the damping factor for a parallel and series resonant circuit. That's the zeta, and it's in the circled area on the left. It's related to the alpha parameter. I'm more used to working with zeta, but you can work with either. Okay. Inductor parasitics. Inductors are not perfect either. You start off with a core. Now the core actually has a magnetic material in it, so that the magnetic flux that you get out of it is going to be more than what you induce in it. You make a little coil of wire, and it makes very weak magnetic flux. that tends to induce changes in the magnetic material. All of their little magnetic dipoles, think of them like little compasses, they all spin to align up with the field that's inducing it, and it creates a much, much bigger field. It magnifies it, so you end up coming out with a very, very large B field for a very tiny H field, or magnetizing force. Okay, so we end up with an inductance, and we have this wire. Well, the wire isn't perfect. The wire ends up having some series resistance, and it's kind of all the way through the wire as shown. And we end up, so that's being shown down at the bottom as RW. Also, it turns out that we have a little finer pen here. I'll probably do. If you're following this curve, your BH loop will probably look something like this for a small current. Every time, you'll notice there's some area inside that loop. There's a little bit of hysteresis in these magnetic materials, and so there's some loss every time you go around this loop. And the higher the current, the more the loop will extend up, but it will still be there. And you'll notice that the because the slope is fairly linear, that the length here is pretty much the resulting B field is again pretty much proportional to the applied H field. Therefore, these loss effects are going to be basically proportional to the amount of current, and that they're proportional in such a way that the best way to take them in, okay, we need to put them in a different place than the resistance of the winding if we're going to talk about a model. So you will have here a whole bunch of little capacitors between the windings. Because these little capacitances exist, you'll find that it's necessary to handle them in some way. How do they express themselves? Well, if you have two windings, if you have a transformer, a unity gain transformer that's tightly locked, you put a capacitor on the output. What do you see on the input? Well, the capacitance on the output is just mapped to the input. You see the capacitance. So the little capacitors on each individual coil all map back to the equivalent of being on the source. So we end up seeing a large capacitor across here that's the equivalent of this device, equivalent of all the little capacitors. And what does this give rise to? Well, this gives rise to the self-resonant frequency. And it turns out that this also is where there's another resistive constant that goes in here. If you want to use that has to do with some of the frequency-sensitive things. Obviously, at DC, what are you going to measure for resistance? You're only going to measure the resistance of the winding. Sorry, that's not RW. At very, very high frequencies, you're going to measure the core loss. You can check, let's say you don't put any DC in, but you pump it at a very, very high frequency above its self-resonant frequency to where the capacitance dominates. In that case, you're going to be measuring all that loss in the core. Okay, so this is an ideal representation of a transformer. I'm sorry, of an inductor. And this is what we're going to look at very shortly. We'll see that the self-resonant frequency comes up over and over and over again. There is a fairly nice site to look at that makes some of these things easy, so I thought we would diverge for a second to show it to you. It's coilcraft. We make no statement about this being we're not linked with coilcraft in any way. There's a number of good sites out there. It's just their tools are fairly simple. They have all their own parts. They have a whole bunch of different types. They sell them. Get this out of the way for a brief second. that you can buy direct from them online. They have all these EMI support tools, which I think I should show, just primarily for a couple of reasons. And they also have step models and splice models for many of those parts, so that if you want to simulate or if you want to actually make PCB parts and fit them into something, it becomes useful. And they've also kind of aligned themselves with 3D Content Central, so many of their bodies are available on 3D Content Centrals. Many of you know that. Okay, so here's one of their tools for basically doing a DC to DC converter in a buck configuration, which is what we've been talking about. You go through and basically put in whatever parameters you want. Basically, what's the nominal input voltage, what's the max input voltage, what's the output voltage. Here's going from 5 volts to 3 volts. Forward voltage on the diode. Again, if you use a Schottky, it'd use a lower voltage. If you use an active rectifier, it'd be lower yet. What's the saturation voltage across your switching device? So if you're using a MOSFET, it's going to be pretty low. Output current that you want to use. Also, what frequency do you want to switch at for picking these? Your question might be, how do we choose those? Well, there's two ways to do it. You can actually do some hard calculations, or you can try something and then try to adjust it afterwards. Okay, how much max ripple current? Let's say we chose these kind of values to see what comes up. All right, so it says, well, okay, here's what it calculated for what is necessary, what would be a good solution. It has 4.11 minimum microhenries, a saturation current of 2.2 amps, but an RMS current, it has to be 2 amps. That has to do with the heating. A duty cycle will be about 0.57, and the peak-to-peak current ripple will be about 0.4 amps. Since they have their parts database online, you can find a suitable inductor. And it will search for them. And hopefully this will only take a moment. If it takes longer, I will back up and try it again. There we go. And so here are a number of components that they have that meet those requirements. Now you will notice that some of these have a some of these actually are unshielded, and some of these are shielded. In general, if you use unshielded parts, that means much of the magnetic flux is going to be fringing out in the area of the inductor. You have to be careful about that. Better to use something that's shielded. So let's choose one that looks like it's a pretty fully shielded one, and let's look at its features. Okay. And here's what came up. I want you to be small again. Okay, so this isn't, I keep putting it up there. What did I do? Made it small. Okay. This is the one I want small. There we go. Okay, I'm going to keep that away from the top. But you see the XAL8080-472 right here. Okay. Note that its self-resonant frequency is 24 megahertz. That means that you have to stay far away from 24 megahertz in any of the harmonic content that's going into this circuit, or it's going to cause resonances that can cause bigger problems. So you probably could run at 1 megahertz, but you certainly shouldn't be running at 10 megahertz switching speed with something that has that self-resonant frequency. And if possible, try to make it so that the if you're up the lower harmonics, like the 5th harmonic or something, doesn't align with the resonant frequency. All right, so let's take a look at that part. So there it is. They have it. We probably could. I don't want that. I was hoping to find. Oh, I wanted to get the PDF. So we already shot it. Anyway, you can get all of these things. I'll give you the curves. You can look at them, mounting dimensions, everything you need. So there we have it. And they also have the other stuff. When you get there, you'll find that they have the SPICE models and also the They have the SPICE models, and they also have the 3D bodies. Okay, so let's back away from this for a second. So how are inductors shielded? That's a question somebody asked. Typically, we're talking usually in inductors about magnetic shielding. They can also have electrical shielding, but usually that's not the problem. Usually it's the magnetic flux coming out of them. If the magnetic material completely encloses the device, such that there's no open place where the wires can be seen, say it goes through a pot core, or there's two pots together, then it is magnetically shielded. That can also form an electric shield. It turns out that toroids are kind of intrinsically self-shielding, because if you take a solenoid coil where all the flux comes out both of the ends, the more you bend the two in a U, you'll find out that most of the lines coming out the ends go to the other ends. That's where they terminate. They form loops, so that if you bend it all the way around a circle, they're actually going around all on the inside. There's nothing on the outside. So if you have a toroidal core, they're intrinsically self-shielding. There's a number of shapes and sizes that are self-shielding, but a number of them aren't. If you have if you have simple open cores, in many cases, you can actually get quite a bit of fringing flux, and then you have to keep a lot of things far away from that. Are the shields connected to ground? Not necessarily. Magnetic shielding does not need to be electrically connected to grounding at all. It's only if you're worried about electrical fields coming off of a coil or something, which can happen. I mean, let's say you have the large voltages on this coil. The whole coil may be going up and down in voltage, the wire itself, and that may radiate, and that may require some kind of electric shielding. Okay, so let's get to the schematics. All right. Let's switch over here. Altium Designer. Okay, here's a buck structure. Let's take a look at the schematic. Schematic is everything we talked about. We have a 5-volt source going into some input filtering and there's a damping resistor and an input filter. This keeps the noise from the buck. It's not classically part of the buck, but it keeps the noise from getting back to the source. So wherever the switching noise is, you probably should put a capacitor right near where you want it to be fed, and then an inductor to block the noise from coming back to your supply. There's the switch. There's the other switch. Q1 and D1 form the switching pair. It's being driven with a PWM very simply at about 0.65 duty cycle. And then you have an inductor and a capacitor. And these are all components. This happens to be Altium Designer, and these are made simulation ready with the various models put into them. So if we want to run that simulation, we can definitely see it. Where's my two? There it is. Okay, and I'm not going to go through the setup because we did that last time. I'll just show it to you really quickly. We're going to do an operating point, a transient sweep, and a pole zero analysis, which doesn't really matter. If I looked at the transient parameters, if I looked at the transient analysis, you're going to see we're going to run for 3 milliseconds. It's got some step time and some other defaults. Okay, so let's run this and see what happens. And then we'll look at the nodes themselves. Okay, so that was the previous plot. Well, it looks like it forgot the last setup. So I'm not sure if we'll be able to easily see this, but we'll let it run. And then we'll go look at the nodes on the PC board. So we can look at a few of these things. Here's the input current. Okay. This is the input current. and it looks like it's settling out at about an amp. Let's see if we can find some voltages or other things that might be interesting while it's simulating. Notice our period of time is about it's about 3 milliseconds. So you can see that the output voltage came up, hovered around 3 volts, and it's stabilizing out at right about 3 volts. Let's see if we can find some. So let's see if we can find there's the input voltage. Well, there was the input voltage. One thing, by the way, when things are switching, you end up finding that it usually takes it takes quite a bit of processing to simulate this much switching in SPICE, so it takes a little bit of time. Okay, I have another question. In each on and off cycle, MOSFET will be on-off, but the body diode needs recovery. The then interaction is important for a FET on. Then interaction is important for FET on and diode reverse. What and how should you proceed? Okay, you want to make sure when you're operating FETs that you do not have a shoot-through condition where both an upper and lower FET are turned on at the same time. If the bottom device is a diode, then all of a sudden you get to a place that it can't conduct in the backwards direction. It can only conduct in the forward direction, which is pointed up, because the inductor is going to continue to pull current up through the diode when the main series FET is off. So what you're going to find is that you can do that and not risk it. If you have two MOSFETs, you have to be careful about your drivers to make sure that that the turn off is slightly quicker than the turn on, or at least that they're switching. You're dragging off enough current out of the gate to turn it off more quickly than you're putting current into the gate that you're trying to turn on. So there's some calculations on that. You can actually put in timing to guarantee it. In many cases, it happens automatically. But you're absolutely right. You do not want to have shoot-through occur. So, okay. Well, you can see on the top curve here that the output voltage is 3 volts. It did settle out. Sorry about that, destroying the curve. Let's take a look at the PC board. First, here's a one-sided PC board. Let's go back into 2D mode so that we can actually look at the insides of the board. Okay, so everything is routed on one surface of this board. Now, if you will look, let's try to see if we can find some critical circuits. What is the switching node? Well, it's this VSW signal. Okay, and it's the switching node is the node in between these three parts. So we go back to the PCB. You'll see there are the 3 parts. You'll see that the node between them is right here. Well, those can't. That node can hardly, the VSW node, is so small you can't really get it any smaller than that. Okay, you'll see that it does have some adjacency to other parts. You could conceivably rotate a few parts to keep it further away, but in general, you're getting about as close as you can. What we'll see in a moment is if you look at a loop, you'll find that C2 and RS2 need to be in the same place. So you don't really want them to get further apart because that's part of the current loop that we're trying to minimize. So if we say, well, where is the current loop? Well, part of the time the current flows through the MOSFET, part of the time through the diode, and when the MOSFET is on, it's actually drawing it. Okay, so it's drawing it up through the capacitor. So that's really the place where the currents are switching. Let's look at that path. So now you can see the two components, C2 and RS2 on the left, are also need to be part of that loop. This is the loop we need to keep small. It's up, through, down, and around. Now that loop has been kept about as small as you can on a one-sided design. Now it is possible to look at a two-sided design, and if you have a two-sided design, let's switch it here to okay. Here's a two-sided design. So if we look at the bottom layer, you'll see that the two parts that we're talking about are on the bottom, and on the top layer you have the two parts that you need to be on the top. Let me see if I can throw this. Here's Q1 and D1, the two switches. If I switch to the bottom layer, you'll see the other two parts in the loop are right there at the same point. So that now those traces have actually been overlapped so that the current flowing and coming are in identically the same place. Okay. Hope that helps. Okay, we have another question. Does diode reverse recovery on the neighborhood of 35 nanoseconds create a current shoot-through? Sometimes, in certain circumstances, it can. Again, they're fairly rare. Most people I know end up using Schottky diodes, and one of the reasons is because reverse recovery is much faster in a Schottky diode because it's a majority carrier device instead of a minority carrier device. Using regular silicon diodes is not as good. They take longer to turn off. So you don't have that same problem of trying to extinguish all the carriers. So most places it automatically does not become a problem. Also, as soon as you chase the carriers out, the current tends to stop. So again, majority versus carrier versus minority carrier. Let's go over and let's see if we can get let's go switch over to the boost technology. Hopefully this is the right one. We'll take a look at a boost topology real quickly here. The same topology restrictions apply to it and just about any others. If you have a node that is switching, you've got to keep it away from anything else. If you have a loop where current is switching from going in one side to the other, find out where that loop is and try to make it occur in the same spot. Oh, okay, I have a save screen up here hiding. That's what was slowing it down. Okay. Too many screens. Okay, let's bring a boost up. Here's the classic boost topology. There's a bunch more topologies. We can talk about those on a later date. We need to take some questions. So if you have questions, please start sending them in. Again, this one, Q1 turns on, build up the current through the input inductor. You turn the Q1 off, and it squirts through the diode into the output capacitor. Since this is transient current surges on the output, we put an output filter on it to reduce the ripple on the output of this device. On the other one, the filter was on the input because we had surges of current on the input. This one is going to be operating in continuous mode, so it'll be having a continuous current draw from the source. But we still have the same type of an issue with the devices. We need to make sure that we keep them. Come on. There we go. Got my hourglass. Okay. We still have to make sure that the switching devices and the switching node are protected. Switching node. So you can see that the node that connects these three components, VSW, is very tight together on this circuit. Again, it's not going to be coupling to much else. Everything else is kept fairly far away from it. So what about the loops? Well, the switching current loop involves those two devices and the rest of the path here. Let's take a look at that. So one time it comes around the bottom through Q1, the other time it comes around the top down through C2. Let's look at that on the PC board. Okay, so you can see the loop here is fairly tight. There's not a lot of area inside this loop for this to kind of radiate. Ideally, they would be laying on top, directly on top one of another, broadside coupled. We can't do that with a single layer type interface. So we can consider looking at it with, if we go to a two-sided board. And we'll reselect those. Two-sided board, now you'll see that the parts are laid on the bottom side are actually directly underneath parts on the top side again, so the two current paths actually overlay each other. All right. We can simulate this if you like. Does anyone have any more questions? Okay. I have a question that I'm not sure I fully understand. It says, am I trying to make two-loop alternate commuting? In general, I'm trying to get the loops in the same place so that the switching current, when it flows down one half of the loop and isn't flowing the other, and then suddenly switches and flows in the other half of the loop, I'm trying to get them in the same place. Let's see if I can show that. If you have current constantly flowing out of the inductor and coming in, we have current in this case that will be intermittently going through the diode. It will be constantly flowing through the output, and it will be constantly flowing through the input. So these do not matter. But what happens is the current is going to sometimes be flowing down through Q1, and the rest of the time, when Q1 is off, it will actually be flowing out through Q2 and back down all the way around. But the part of the loop that's switching in and out is Q1. The rest of this current kind of remains constant. What we're trying to do is to make it to where the current that flows down through here continues flowing right there. So if this diode and this switch are laying right on top of each other, ideally you get it to where when this current stops, that current takes up there, but they're ideally trying to flow in the same physical space down adjacent broadside tracks. So the net effect is the current continues to flow. And to do that, it's necessary to make sure that you find that this is a common junction point where it switches from going down to going over. But that's what we're trying to do, is make the loop so that it doesn't create a problem. Ground bounce. Yes, ground bounce is a phenomenon that occurs usually at very, very high frequencies, especially on digital circuits. I'm not sure it's as applicable on these circuits because we're talking about down in the megahertz-ish range, okay? But there's actually impedance in the ground plane, and there's impedance in pins. And when you try to drive an output pin rapidly to turn something on or off, you with a very, very fast device, it will need to get that current from somewhere, or source or sync it from somewhere, and it can actually do it to the pins on the package, is where it normally gets it from. And if those are not extremely low impedance to ground, then they will actually have a voltage that will, the pin will actually not be at ground. It can actually move up or down, and it can move up and down in some cases by as much as the switching voltages. So it occurs. One of the reasons for having very, very well bypassed ground planes, especially on high-speed digital signals. Now, that's normally the subject of this particular topic, but yes, it will. You can have that. What about current change going through the vias? Absolutely. A very, very rapid current change going through vias. The vias have an inductance, and therefore you will see a large voltage develop across the inductance of that via shortly, and then the current will start to flow, and then it will collapse. So the spikes of vias is a problem. So you have to ask, are the switching speeds that we're going through with the devices in question here in this power circuit going to be causing that type of a problem? The answer is probably not to a significant degree. You can calculate it, but again, we're down in the neighborhood. Remember, these are huge devices. They do have a lot of current. I mean, this is a 100-amp device, but their turn on and off times are, I doubt that they will be really turning on and off in, I don't know. They might be turning on and off in 10 nanoseconds if they were really, really fast, but I don't think so. I think it's going to be slower than that. I'd have to look up the spec to see. So the rate of change of current is much lower because the device is so big. The inductance is low because the vias are huge, which helps lower the inductance of the via, and just because it's so big and it just can't move that fast. And again, that's one of the reasons why if you start saying, I want to build a switching power converter and switch at 100 megahertz, you conceivably could do it, but all of these other effects would start coming into play. If you're switching down in 100 kilohertz, almost nothing comes into play at a megahertz. Yes, you can start thinking about it. 10 megahertz, you should probably start thinking about it. One way to ask yourself a question is, what is a quarter wavelength of the highest significant frequencies involved? When things become a quarter wavelength, when your frequencies are high enough that your features are a quarter wavelength long, you have severe problems. If you stay a couple orders of magnitude away from that, you probably won't. There's lots of ways of looking at it, but I just think that would be, I don't think ground bounce is really going to be a significant problem here, but it would be worth looking at. What about current going through the vias? Current going through the vias, yes, that will cause a drop. The question is the rate of rise of that current. Is that current, look at the VDT, compare it with the inductance of a typical via, especially that diameter via, and see. If the vias are shorter, it makes it better. If this was a very thick board, of course the inductance on the vias would be higher. I don't have a calculation on that, but okay. Another question: Would the via need thicker plating? It would need enough plating to be able to carry the current over the distances that it travels. If a via is very thin, let's say you only were using a 5 mil thick layer for a top and bottom of 2 current layers, then the via would probably be so short, its barrel would be so short in length, at least the current carrying portion, that wouldn't be a problem. But if you have a 16-inch thick board, well, that entire length has to be carrying that current. You want to make sure that that has as much cross-sectional area as the traces in the board, which I'm sure you've already calculated to be able to handle that amount of current. So yes, you need to make sure that you have adequate cross-sectional copper for all the vias in the hole. Rather than having very thick copper in the hole or studs in the hole, you may choose instead to have an array of vias. That's commonly done. Please explain about dot convention on inductor. A single inductor, it's not important to have a dot convention. It tells me what pin 1 is. It helps me in simulation. If you have an inductor that has multiple windings on it, which is not uncommon, then it's important to know how the polarities relate to each other. So it's kind of a moot point in a single inductor that just has 2 pins. But it's not just a transformer convention. It's an inductor and transformer convention used to identify the same polarity pin on all the coils. In this case, I only happen to have 1, so it's kind of a moot point. How no vias on two-sided design affect path impedance, resistance, inductance? How do vias on two-sided design? Yes, again, you're always trading things off in design. You are going to be going through vias. I would not recommend smattering all the parts on 2 sides just because they fit conveniently. I would minimize your paths on 1 side. In this case, there were only two parts pushed to the back side, and those were specifically there to try to minimize current paths. So it was an optimization to go to two sides. I would recommend, if you can do your design on one side really cleanly, that it would be beneficial to do so. And you could have a ground plane under it to help shield everything. Two-loop current flow together. That's only because the current flows in one half of the loop half the time. It flows in the other half of the loop the other half of the time. So if you organize it properly, you get the current flowing in the same general path all the time. There's no change in current. That's why you do that.